All right, so first thing we'll do is we'll finish up section 5.1. Okay, so yesterday we talked about how to convert from polar to rectangular. Okay, today we're going to start off with the reverse. So just to make sure we remember what they give us, if you're given a point in rectangular using that system, what are the two things that they give you? A what and a what?
Cosine and sine.
This is like if I was going to describe a location in rectangular, I would have to tell you the blank value and the blank value.
X and Y.
Yes, I'd have to tell you the x and the y value. So they're going to start you off with an x and a y. And in polar, what are the two letters that we're going to end up with? We're not going to have x and y anymore.
R and theta.
R and theta. Okay, so a typical problem is going to look like this. There's an x and a y value. Change it to polar. All right, so let's draw out what we have. Okay, when we set up this kind of diagram yesterday, does anyone remember what shape we ended up sketching?
Triangle.
A triangle. Okay, and right now you know two sides of the triangle. You know how far to go from the origin over to right about there. That's the x distance. And y is the height. That's how far you go from this point up. Right, so we need the r and we need the theta. Okay. If you're wondering, well, how would you have r? Think of it like this. Think of that point as being on the edge of a circle. When I draw this segment in, that's r, but it's also the what of that triangle? It's the hypotenuse. So we have to find r, but we're going to know x and y, so we'll talk about the theorem we need to use in a second. And the other thing we have to find is theta. We need to find r and theta. So everything in red is given to you. Everything in black you need to find. I'm going to write it out nicely on the next page. But for now, can someone just tell me, how would you find r if you know x and y? Yep.
Pythagorean theorem.
You just use the Pythagorean theorem. Okay, so we'll write that down in a minute. And the next thing we have to find is theta. Well, if you're going to use this and that, x is adjacent, y is opposite. What trig function would have opposite and adjacent in it? Yeah, tangent. Okay, so I'm going to write it down kind of quick here, but I have it written really nice on the next page. So if you just watch this for a second, you're not going to miss writing anything down. So the tangent is opposite over adjacent. But the problem with that is that's not theta. That's tangent theta. Does anyone remember how we get rid of tangent? Yeah? Inverse tangent. So we take the inverse tangent of each side, and that is the formula for theta, okay, which I'm going to write down on the next page. Okay, so that's kind of the two things you need to know. Inverse tangent will help you find the angle. Pythagorean theorem is how you get the radius. And then we can change it into polar. All right. So first thing we want to make sure we know is when we're going to change it to polar, we want to know the quadrant that it's in. Okay. So just to be clear and make sure people remember the quadrants, those are how the quadrants are numbered. 1 in the upper right, 2, 3, 4. Okay. If you can determine the quadrant without graphing it, technically that's fine. The real goal in step 1 is just make sure you know what quadrant you're starting, because that's going to be important. All right. Once we know what quadrant we're starting in, then we can find the first thing. We can find the angle. If you want to do the radius first with Pythagorean theorem, you can. They're separate. You got to do both. So pick which one you want to do first. I'm going to do theta first. If you're in quadrants 1 or 4, you do exactly what I just showed you on the other page. It's the inverse tangent of y over x. But the problem with that inverse tangent is if you type something in and press inverse tangent and then hit enter on your calculator, the number that your calculator gives you is always going to be between two values. It's always going to be between negative 90 and positive 90. So that means when you type in what's in that box and hit enter, you're either going to get an answer in quadrant 1 or quadrant 4. It's impossible for that formula to give you an answer in 2 or 3. It doesn't. It never would. But you could definitely have coordinates in 2 and 3. Like, say you had the coordinate negative 5, 8. Left 5, up 8. That's in quadrant 2. So that formula won't quite work in quadrant 2. So we have to make a small adjustment to it if you're trying to work in quadrants 2 or 3. So if you're in quadrants 2 or 3, all you have to do in front of the formula is add pi if you're doing it in radians, or 180 if you're doing it in degrees. And what that 180 plus 180 does is it forces the formula to give you answers on the other half of the circle in these two sections. Okay, so you don't need to add the 180 if you're in quadrants 1 and 4, just 2 and 3. All right, so now you've got a formula to find the angle if you're in quadrant 1, 2, 3, or 4. But where else could you be besides quadrants 1, 2, 3, and 4? Yeah.
The center.
Well, you're always going to be somewhere. Pretend that this is a circle. You're always going to be on the perimeter of a circle somewhere. So unless you had a circle with a radius of 0, which I would never give you, because that doesn't really make sense, you don't have to worry about that. Anyone else have a thought? Where else can you be besides in quadrants 1, 2, 3, or 4, just looking at that circle?
On the axis.
You could be on an axis. Okay? And the problem if you're on an axis, let's pretend I gave you this point. And I wanted you to convert that to polar. Well, what's the x value of that coordinate?
0.
It's 0, because it's on an axis. How far up is it? I don't know. It's up. 2 units, 5 units, whatever you want it to be. But the point is the x value is 0. Look at what happens if you plug 0 into either one of those fractions. You would have a 0 in the bottom of a fraction. Are you allowed to have 0 in the bottom of a fraction? No, that would be dividing by 0. You can't do that. So that's why these formulas only work when you're in a quadrant. If you're on an axis, you just have to memorize it's one of those 4 answers. Okay. If you're on the right part of the axis, it's 90. If you're on the up part, it's 90. I'm sorry, if your right part is 0, up part is 90. If you go left, it's 180. If you go down, it's 270. Now we've covered everywhere that you could have a point, in a quadrant or on an axis. Some people get mixed up when it's on an axis because they forget, but that's actually the easiest case. You don't need to use inverse tangent at all if you land exactly on one of those 4. Okay. So any questions on finding the angle? Okay, and then once I find the angle, what's the other thing you need in polar besides the angle? The radius. And what theorem did we say we're going to use to find it? Pythagorean theorem. That formula is the same no matter what quadrant you're in. So it's just Pythagorean theorem written with an x, a y, and an r instead of a, b, and c. Okay, so we'll try an example or two of changing to polar, and then that'll be it for section 5.1. All right, so I've got the point 2, -2. Okay, so let's put up our steps. Step 1, graph the point, but really you just need to know the quadrant it's in. That's So, Caitlin, can you tell me what quadrant 2, -2 would be in?
4.
Yep, 4. It's right 2, down 2, somewhere right around there. Okay, so now to find theta, I'm going to look at my formula for quadrant 4. Cassandra, if I'm in quadrant 4, is that the one where I have to add the 180 or no? No, don't have to add it. So it's inverse tangent. And Luke, what's going to go in the top of my fraction? -2. And the bottom?
2.
2. Okay, so type that in and see what you get. Now, if we want just to kind of save us having to press a few buttons, what's -2 divided by 2? -1. So I can just type the inverse tangent of -1. And I get -45. So that's my angle. All right, so that's half of what I need. Got the angle. Last thing I need is the radius. So to get the radius, we're just going to fill into that formula and see what we get. Okay, so we got r squared equals, and Pacey, can you fill in the rest of it for me?
4 plus 4.
Yeah, and can you even go back one step? That's going to be what it simplifies to, but how did you get 4?
-2 squared plus 2 squared.
Perfect. -2 squared plus 2 squared. So he did y squared plus x squared. That's okay. It doesn't really matter if you switch the order of x and y when you're adding. 2 plus 6, 6 plus 2, same thing. So we get r squared equals 4 plus 4, which means r squared is 8. So r, how would you get r by itself? Yep. Take the square root. So it's the square root of 8. Or we always have to reduce the square root if we can. What is the square root of 8 reduced to?
2.828.
So if you change it to a decimal, it might ask for that, which is possible. So if it does, you can put that 2.828. But if it asks you to leave it exact, we just want to reduce it without changing it to a decimal.
2 square roots of 2.
2 square roots of 2. Any question on how she did that?
Yeah, how'd you do that?
So there's a lot of ways to do it. Some people make like a factor tree. The way I do it is I break up the number 8 as something times something. And you try to break it up so one of the numbers has a square root you can do. I would break it up like this. You can break 8 up into 4 times 2. And then take the square root of each number separate. Square root of 4 times the square root of 2, which is 2 square roots of 2. Okay. Again, you can do like a tree or other things. So like if you had like the square root of 20. Now you could break that up into 10 times 2, but that's not going to help. You can't take the square root of 10 and you can't take the square root of 2 in your head. A better way to break this up, 4 times, I don't know what, my elbow is hitting the screen as I'm trying to write. 4 times 5. So now you get the square root of 4 times the square root of 5, which is 2 square roots of 5. Okay. So some of them you do have options, like 10 times 2, 4 times 5. You got to pick the way that would work better. All right. So now let's write our final answer. R, comma, theta. There's the coordinates of that point. Now that's with a positive radius and a negative angle. How many basic ways are there to get to every point in polar?
4.
4. So that's one of 4 different answers you could write. Okay. And we went through yesterday how to get all the other answers if you're given one. So any questions on how you would write this with, say, a positive radius and a positive angle? If I asked for that. This one you just add 360. So 2 root 2, comma, 315 would be how you would write it as a positive. Okay. And then we could do negative, and all the other stuff. Great. Questions on that one? So let's try this one. -4, -5. Okay, so Sean, what's the first thing I want to know about that point? Before I even really start any calculations.
What quadrant?
Yeah, just figure out the quadrant, and then that'll tell me the formula I need to use. So what quadrant is that?
Number 3.
Yep, it's left 4, down 5, so somewhere over there. And if I'm in quadrant 3, is that the one where I have to add the 180?
Yeah.
Yes. So theta, if you're doing it in degrees, if you want to do radians, you'd put plus pi. 180 plus, and Kyle, can you tell me what would go inside there?
-5 over -4.
Yep, it's -5 over -4. When I type that in, I'm just going to cancel the negatives. I'm just going to type in 180 plus inverse tangent of 5/4. So 180 plus inverse tangent, 5/4. So we don't get a very nice angle here, so that we'll just round it. 231.34. So there's my angle. And last thing I need is my radius. Luke, can you set up my equation to find the radius?
R squared
Yep.
equals -4 squared plus -5 squared.
Plus -5 squared. Okay, when we do that out, we're going to get 16. Okay, you should never get a negative here because you're squaring things, so the numbers are always positive. 16 plus 25. Add those up. Gives me 41. And Brianna, my last step would be
2 square root.
take the square root. Okay, so there's my radius. So we'll write the final answer. We've got R, comma, theta. Now, it's kind of weird if you're going to write something as a decimal and then leave the other one exact. That's kind of weird. If you're going to put a decimal for the angle, you're probably just going to put a decimal for the radius as well to be consistent. Any questions on how you change square root 41 to a decimal? It's like 6 point something. But that's fine. We can just leave it for this. Okay. So any questions on 5.1? Okay, so that was the last thing there. All right, so now we're going to, it's going to feel like we're kind of switching gears a little bit because we're going to talk about complex numbers. But on Wednesday or probably Thursday, you're going to see the connection between what I'm doing now and what we just learned over the past day. Okay, so this is in Appendix 4 in the back of the book. So Appendix 4 starts off with what complex numbers are and the definition, but I kind of want to take a step back from that and just explain why we even have them. Okay, why do you need complex numbers? Because they're kind of something most people don't understand where they're used in real life. They're not used very often for most average jobs, even, you know, unless you're an engineer or something like that, you're not using complex numbers in everyday life. Okay, but I'm just going to try to show you why they exist. That's all. Not necessarily where you use them. All right, so to do that, I'm going to start out with just explaining the different kinds of numbers we have, going from the simplest to the most complex. So the simplest kind of numbers that we start out with are your counting numbers. So counting numbers, what do counting numbers start with? What's your first number if you're counting?
0.
So if I was going to count the people in this room, would I go 0, 1, 2, 3,
Yeah.
4?
Yeah. I'm sure.
You start with 1.
I go
So counting numbers, there's no such thing as 0. So pretend like you forget everything you know about numbers right now, and I'm telling you all that exists is counting numbers. Counting numbers start at 1, and they go up by, wholes, no decimals. 1, 2, 3, 4, 5, 6. So where we run into a problem with counting numbers is when we start doing arithmetic. Addition is not a problem. if you take a counting number, like Pacey, give me a counting number.
4.
4. Plus. And Kyle, give me another counting number.
9.
9. If I add those two counting numbers together, I get 13. Is that a counting number, 13? Yeah, works perfect. And that will always work. You could give me any counting number you want plus any other counting number. We never have an issue. But let's change one thing. Instead of plus, let's make it a minus. 4 minus 9. Now we know what the answer is, but is the answer a counting number?
No.
No. So if you don't understand negative numbers, or even something even a little simpler, even this is a problem. It's not even negative, but if all you understand is counting numbers, you can't do that. 5 take away 5 is something that doesn't even exist yet. So what they have to do is invent a new number to represent the answer to that problem. And that's what they do. They invent the number 0. All right? So you might think, well, didn't 0 just always exist? No. There was, if you look it up, like if you're really interested, the history of 0, at one point it was kind of just invented, the idea of having nothing. And that adding 0, we now call this a whole number system. So now with whole numbers, you have a thing, and it looks like this, that represents the idea of nothing. And that's the symbol we use. But even with whole numbers, we can still run into a problem like the one we have right here. 4 take away 9 is not a whole number. What kind of number do you get if you do 4 take away 9? Negative. Those don't exist. So if I ask somebody in like first grade, what's 4 take away 9? They might just put a question mark. If they were really intelligent, maybe they would write like undefined, but probably not. But you can't do it. So then we invent another kind of thing to represent negatives. Okay? And this little symbol, when you put it in front of a number, represents having less than nothing. Okay? It's negative. And we call, does anybody know what we call this number set when we include negatives now? Begins with an I.
Imaginary.
Not imaginary yet. We're 4 or 5 steps away from there. So we're going to get there, but we're still pretty simple.
Integer.
Integers. Yep. So now, integers solve a lot of problems. You can do any kind of addition you want. You'll never run into a problem. You can do subtraction. Okay? 4 minus 9, we could do. 12 minus 13, 16 minus 0. You can do any of those calculations. Multiplication would also be fine. But division, we could run into a problem. Can somebody give me an integer divided by an integer, and the answer is not an integer? Yeah?
4 divided by 0.
All right, so dividing by 0, that's a whole other problem, which I'm not going to get into too much, but we can never divide by 0. But let's try something that's not a 0 in the bottom. That's still a problem here. Yeah?
5.
4 divided by 5. Yes. So now what you're asking me to do is to take 4 objects and give them out equally to 5 people. I can't do that. The only way I can take 4 things and divide it to 5 people is if I start breaking things into pieces. Okay? And I take parts of things. So in order to represent having parts or fractions of a whole, they invent a new kind of number called decimals or fractions. So now we have the idea of representing parts of things, and those are your rational numbers. For most everyday purposes, most people don't have to learn or use numbers that go beyond rational. When you're pumping gas, you might get $8 and it might stop. If you just fill your tank, it might stop at $8.17 if you only need a little bit of gas. Okay? But it's 8.17, 17 hundredths of a dollar. If you're measuring something, even if you're measuring in like the machine shop, they're very accurate. They may be accurate to the 10,000th or even 100,000th of an inch, but that's still a rational number. It doesn't go on forever. Okay? Rational numbers stop somewhere. They don't go on forever. If you're cooking, maybe you need 2/3 of a cup of flour. Okay? That's a rational number. You don't need a whole cup, you need a fraction of a whole cup. But there's numbers that go beyond rational, and now we start to get into things that are less used in everyday life. Does anybody know the kind of numbers that are not rational? What those are called? Yeah? Yeah?
Irrational.
Irrational. So, where do irrational numbers come up? Well, if you want to take a square root of a number, like 4, that's fine. But if you want to take the square root of 5, if all you understand is rational numbers, you would have to say this is undefined. You cannot do it. Because there is no way to write the square root of 5 as a fraction. I could prove that to you. I'm not going to, but I could. You cannot write the square root of 5 as a fraction ever. So if all you understand is fractions, then you're never writing the answer to this problem. So that's why they, again, invent another kind of number called irrational. Okay? Pi is an irrational number. Okay? They've written pi out to many, many, many decimals, way more than it's up there. And they've never found a pattern. It never ends, it never repeats. So we call that an irrational number. And square roots is where they come up most often. Other kinds of numbers that are, well, actually, we'll just leave it at that. Okay, so irrational numbers mostly come up with square roots and pi. Now, if you take and group all of this stuff together, these are called real numbers. And in Algebra 1, that's what you study. You don't do anything in Algebra 1 that's outside of this box. And also, just to kind of explain how these blocks work and why I have one inside the other, if you think of them as places, okay, this will make sense in a second. Think of counting as a very specific place, let's say Boston. And then let's get more and more general. So as we go out to whole numbers, we get to Massachusetts. Integers could be the Northeast. Rational could be the United States. Real numbers, Earth. Okay? Let me give you an example. If you are in Boston, are you in Massachusetts?
Yes.
Yes. If you are in Boston, you are automatically in Massachusetts. Forget there might be a Boston in like Kansas or something. But if you're in Boston, you're in Massachusetts. Look at it the other way around. If you're in Massachusetts, are you automatically in Boston?
Yeah.
No. That's how this chart works. If you are a counting number, you are automatically a whole number because you're also inside that box. But if you're a whole number, you're not necessarily a counting number. All right? So that's how it works. If you're in Boston, you're automatically on Earth. If you're on Earth, you're not automatically in Boston. Well, there's something beyond Earth. Okay? You can think of it as other planets. Okay? We have real numbers, and we also have imaginary numbers. Now, at each step that I've gone, I've tried to explain to you, well, if you don't believe in 0, you can't do this calculation. If you don't understand negatives, you can't do 6 minus 10. Well, if you don't believe in imaginaries, you can't do that. If I asked somebody to do that in Algebra 1, they would say undefined. You cannot take the square root of a negative number. Okay? Let's try it on the calculator. Let's try to take the square root of -4. Okay, calculator gives me an error. You can't do it. And it's not that it can't do it because the answer doesn't exist. It can't do it because I told the calculator to only use the real number system. Okay? So it says real right there. So if the calculator thinks, okay, real numbers are the only kinds of numbers that exist, and the answer to this problem is not a real number, the calculator is going to say, wait a minute, I can't do it. So if I basically teach the calculator about imaginaries by changing it to that mode, and tell the calculator, okay, you know what? Do the same problem again. Now the calculator says, okay, I believe in something beyond Earth, right? I'm going beyond real numbers to a new kind of number called imaginary. And that's why they have to invent imaginaries. Without it, you can't take the square root of any negative numbers. Okay? And together, these two things form the big set of numbers that we call complex numbers. Is there anything beyond complex numbers? Not that I'm really aware of. Okay, that's as complicated as we get. Everything we do falls under that big umbrella of complex numbers. Think of complex numbers as the solar system, right? Maybe there's some stuff beyond that. In fact, we know there is. But think of complex numbers. That's the big thing. And then everything falls under it. Okay? So that's kind of the layout of this section. Okay, so that's where we're going to start off with, talking about the definition of a complex number. So complex numbers have two parts to them. And I tried to show you in that diagram. They have a real part, and they have an imaginary part. And if you write a complex number in this way, so an example would be something like 2 plus 3i. That's called the standard form of a complex number. You always put the real part first, the imaginary part second, and the imaginary part is just the b. The I is next to it to tell you, hey, the thing in front of me is imaginary. Now, I already said, as far as uses of complex numbers, we don't get into any applications at all. Okay, we don't do that. If you are in engineering, I know they do talk a little bit about complex numbers because I've asked people in the past. Is anybody in engineering? No? Okay. So there are some uses, but the uses are very, very limited. Okay. All right. So in that particular example, I'm just showing you the real part of this number is 2. The imaginary part is 3. So any questions on how to identify what the real part is, what the imaginary part is, and what standard form is in that order? So I haven't really talked to you about I at all. Now, you might think of I as a letter. And in some context, you are correct. I is a letter in the English alphabet. Well, as an example, you might also think this is a letter. It is. It's a letter in the Greek alphabet. But in math, that is not a letter. Even though it is a letter in the Greek alphabet, you would never use this as a variable in math. Why wouldn't we use that as a variable? Yeah.
It has a value.
It has a value assigned to it. 3.14. It keeps going. Well, in math, you would never use I as a variable. Why? The same reason. It has a value assigned to it. Okay? There is a certain thing that I is equal to. This is equal to 3.14. This is equal to something, which I don't need to tell you right now, but I will towards the end of the lesson. Okay? But you have to kind of get the idea of I as a letter out of your head. Okay? I is going to be assigned a value in this lesson. Okay? If you have a number that doesn't have a real part, like 4i, negative 2i. Those are called pure imaginary numbers. If you want, you could think of it as 0 plus 4i. The real part is 0. Imaginary part is 4. Generally, if one of the parts of a complex number is 0, we don't even bother writing it. And we would just put that. Okay, so no real part, that's called a pure imaginary number. So really, the only thing we're going to do with complex numbers is learn basic arithmetic. How to add, subtract, multiply, and divide. 2 of those things we're going to do today. 2 of them we'll finish up with tomorrow. There's a lot more stuff you can do with complex numbers. Basically, for example, you can take calculus. You've probably heard of calculus. Well, the kind of calculus that we teach here, you know, calculus seems advanced, but there are more complicated versions of it. We teach the more basic version, and they do everything with real numbers. Well, when you get to college, you can do calculus all over again if you want to have a really great time. And when you do it over again, you do it with imaginary numbers. And then things get a little more interesting. So imaginary numbers basically double the amount of things you can learn. Because you can learn everything with just, you know, real. And then you can do all that kind of stuff again with imaginary. All right? And we're doing the very, very basic stuff, just arithmetic. To really learn all about imaginaries, it would be a whole class, like a whole semester class, just like this. Start in January, end in June, just on imaginary numbers. Okay? So there's a lot of stuff. So first thing I'm going to explain might seem like a simple idea, but just what it means for two complex numbers to be equal to each other. So let's say those are my two complex numbers. A, B, C, and D would all have values. In order for those complex numbers to equal each other, I want you to think of looking at it in parts. This is the real part of the first one. That's the real part of the second one. Those two values have to match. That's the first thing. The real part of the first number has to match the real part of the second number. The second thing is the imaginary part of the first number has to match the imaginary part of the second number. So it might just seem a little common sense, but that idea doesn't come up if I ask you, does 3 equal 3? Yes, there's only one thing you have to check. Does the number on the left match the number on the right? With complex numbers, there's two things you have to check. The real number on the left, the real number on the right. The imaginary number on the left, imaginary number on the right. So I'm just trying to get that idea across. There's two things to check. So for example, 3 plus 8i and 3 plus 8i, those are equal. 3, real parts match. 8, imaginary parts match. Now, if I did something like that, and we check it, 3 matches 3, so the real parts match, but now the imaginary parts don't. So these two complex numbers are not equal. Okay? Even though the first part is. You can't say, well, they're half equal. No, they're not equal at all. The first parts and the second parts have to match. Okay. Any questions on that? Okay, so that's what it means for two complex numbers to be equal. The two arithmetic operations we'll look at today are adding and subtracting. So you would be given two complex numbers separated with a plus sign. They don't have to put parentheses around it, but I just did that so you could clearly understand A plus BI is the first one, C plus DI is the second one. And to add complex numbers, you can kind of think of it as like combining like terms. You are only allowed to combine real numbers with real numbers and imaginaries with imaginaries. You can't mix them. Just like you can't mix 3x plus 2y and say, oh, the answer is 5x. No. The only way you get 5x is if they're like terms. So looking at this one, Brianna, what's the real part of my first number?
A.
And what's the real part of my second number?
C.
So you are allowed to combine the A and the C. So you do that first. Add the A and the C. And then you look at the imaginary part of the first number, B, imaginary part of the second number, D, and you are allowed to combine B and D. And you got to make sure you put an I next to when you combine B and D, so the person understands that that was the imaginary part. And it still is. Okay. The only time you don't need to put an I is if the imaginary part comes out to 0. If it comes out to 0, you can just leave it off. Okay, so that's the idea of adding complex numbers. Okay, think of it as combining like terms. Right, so let's try this one. 3 plus 8i plus 8 plus 2i. Right, so Caitlin, what's the real part of my first number? 3. Cassandra, the real part of my second number? 8. Those can be combined together. And Luke, what do I get when I combine the real parts? 11. So in my final answer, 11 is the real part. Liz, what's the imaginary part of my first number?
8.
Yep, 8. And Jill, the imaginary part of my second number? 2. We can combine the 8 and the 2 together. And when I combine those together, Brianna, what do I get?
10.
Yep, make 10 I. And that's the answer. 11 plus 10i. Any questions on that? Let's try another one. So we've got 4 minus 2i plus 3 minus 8i. So take a second and see if you can figure out what you get when you add those together. Right, so Emma, can you tell me what you got when you added those up?
I got the 4 and the 3 add up to 7.
Yeah, so the real part is 7. I agree with that.
And then for the second part, I got -10.
Yeah, you got a -2 plus a -8. That's a -10. But make sure we let people know that that's imaginary, so we put an I next to it. So 7 minus 10i. And there are no letters in that. Okay, there are no letters in that. There are no variables in that. That thing that I just circled, that is a number. Okay. Questions on that one? All right, try one more with addition, and then we'll go to subtraction. So we get -3 minus 4i plus -7 plus 8i. Right, so Pacey, when I combine my real parts, what do I get here?
-10.
Yep, -10. And Sean, when I combine the imaginaries, what will I get there?
4i.
Yep, 4i. And when I say combine, we are adding. So I should, to be more specific, I could say what we get when you add them. Because we'll do subtraction next. Any questions on that? Okay, so that's adding. Subtracting is pretty much the same thing, except you have a minus sign between the two complex numbers. And here, putting in parentheses, I think, will remind you of something that you need to do. You have a minus in front of parentheses. So this minus is distributed. So when you do the calculation out, it's A minus C. So you have to subtract those two. But then the part some people forget is you have to subtract the other two. B minus D. And then we put the I next to it. Okay, so remember that that minus applies to both the real and the imaginary part in the second number. Okay, so we'll try a few examples of subtraction, and then I'll finish up by telling you what I equals. I told you I is assigned a value. I'll tell you what that value is in a minute. But notice you can do all this stuff without even me really telling you what I is. Okay? I'm showing you that because you don't need to complicate addition and subtraction with understanding what I is yet. Understanding what I is great if you want to get really theoretical, but it's not super important for adding and subtracting. Okay? Okay, so let's try this one. We've got 4 plus 12i minus 3 plus 4i. Okay, how about Marisha, what would I get for my real part?
1.
Yep. 4 minus 3 gives me 1. And How about my imaginary part?
8i.
Yep. 12i minus 4i is 8i. So 1 plus 8i. Okay. Any questions on that? Now, I don't think I've mentioned it yet, but let's say you got an answer like this. 6 plus I. What number is in front of I, even if I don't write it? 1. So the imaginary part there is a 1. Okay. Just like if you have an x, you can pretend like there's a 1 in front of it. Same idea. All right, let's try this one. So 3 minus 5i minus 8 minus 6i. So how about Caitlin? What is the real part?
3.
Yeah, so the real part here is 3, and then in the second number?
8.
8, and if you subtract them?
-5.
Yep. So -5. And then in my other, my imaginary part, I've got -5i minus -6i. So Cassandra, what would -5i minus -6i be?
-11i.
Careful. If you had this, I would agree with you. That would be -5 minus 6. But it's -5 minus -6.
Plus 1i.
So it's going to be turned into a plus. Yep. So -5 plus 6 is 1. So you can put 1i, or you can put what I just talked about. You can just put plus i. Okay, so follow all the same rules that you would with subtraction if you subtract a negative. Okay, questions on that one? All right. So let's type something in on the calculator and see what we get. So when I type in like 9 minus 5 and I hit enter, I get a number. Okay. Anytime that you use these operations and hit enter, the answer on the screen is always a number. Well, if I type in the square root of -1, when I hit enter on the screen, the calculator is going to give me a number. And the number that it gives me is I. Right? It gives me the number I. So I told you it was assigned a value, like pi equals 3.14. I equals the square root of -1. Now, if you asked me why, I would say because. And if you said because why, I would say because. It's a definition. It's kind of like if you asked me, why don't parallel lines cross? Because they don't. That's the way it is. You have to have some things that just are the way they are, and you can't prove it or explain it. That's called a theorem, right? Or not a theorem, that's a postulate. So in geometry, there's 5 basic postulates that you never prove. One of them is that 2 parallel lines never cross. You can't prove that. It's just the way we define it. Okay? It's kind of like saying, why does the color red look like that on the flag? Well, I don't know, because that's what we call red. Just that's the way it is. So same thing here. I just is the square root of -1. There's no explanation or proof why. But using that fact, we can then build off of it. So what does I to the second power mean? Like pretend you're trying to explain that to somebody that doesn't understand what a power is. How would you explain what I to the second power is? Yep.
I times itself.
It means to multiply I times itself as many times as you see the number. So I squared really means I times I. Well, I is the square root of -1. So we could think of it this way. The square root of -1 times the square root of -1. What would you get if you multiplied those two things together? The square root of -1 times the square root of -1. Yep.
Square root of 1. No, 1.
Let's try it with something a little easier. The square root of 9 times the square root of 9. What do you get there? 9. Okay. If you did the square root, I'm just picking easy numbers, the square root of 25 times the square root of 25, what do you get?
25.
You get 25. The answer that you get is whatever is sitting right there, or right there. So what's the square root of negative 1 times the square root of negative 1? Negative 1. And that's very important. So when we get into multiplication, I squared is going to come up a lot. If you ever leave I squared in a final answer on the test, I will mark it wrong. Because I squared can be simplified to the number negative 1. You can also do that on the calculator. I can take I can square it, and you can see the answer I get is negative 1. Okay? So keep that in mind. I squared equals negative 1. Now, if you're wondering, could you keep going? Could you do like I cubed, I to the 4th, I to the 5th, I to the 6th? Yeah, you can keep going. There's a pattern to the answers you get. They just keep repeating. But as far as what we're concerned with, you only have to understand what I squared is. Okay? Any questions on that? Okay, so I think that is a good stopping point for where I want to stop with complex numbers. Tomorrow we'll pick up with multiplying and dividing complex numbers, and then start our last section. Okay, so homework tonight on 308. That's the conversions between rectangular and polar, 55 to 65 all. And 560, that's the complex numbers adding and subtracting, 9 to 14 all. Okay, don't forget I will be after school tomorrow if anyone needs extra help. And we'll have our second to last test for the course on